Grounding requirements for a 100W backup generator with 500 Ohm copper conductors and a 3-pole transfer switch are detailed here. The electrical system must be grounded in accordance with the National Electrical Code, or NEC, and local codes. Since the transfer switch has isolated lugs for neutral, the system must be grounded using an isolated ground rod. Connect a grounding electrode conductor, or GEC, from the isolated ground rod to the generator frame. The GEC must be sized in accordance with NEC Table 250.66 and must not be smaller than the generator grounding electrode conductor. All metal conduit or raceways must be grounded using an equipment grounding conductor, or EGC. The EGC must be at least 500 Ohm copper and must be securely connected to the conduit or raceway. Connect an EGC from the isolated ground rod to the neutral lug of the transfer switch. Connect an EGC from the neutral lug of the transfer switch to all equipment connected to the generator, including the electrical panel and appliances. Bond the isolated ground rod to the building's grounding electrode system, or GES, using a bonding jumper. The bonding jumper must be sized in accordance with NEC Table 250.104 and must be installed in accordance with NEC Article 250. The 400 amps breaker head of the transfer switch provides overcurrent protection for the generator and the connected equipment. The breaker must be sized in accordance with the generator output and the electrical load requirements. Once the grounding system is installed, verify the ground resistance using a ground tester. Also verify continuity between all grounding conductors and proper labeling of all grounding points. System grounding involves ensuring that the generator and associated equipment are safely connected to the earth, providing a path for fault currents and minimizing the risk of electrical shock. Generator grounding specifically refers to connecting the generator frame to a grounding electrode, ensuring that any fault currents are safely directed to the ground. Conduit grounding focuses on grounding all metal conduits and raceways to provide a continuous grounding path. Equipment grounding involves connecting all electrical equipment to the grounding system, ensuring that any fault currents are safely directed to the ground. Bonding involves connecting different parts of the grounding system together to create a low impedance path for fault currents. Breaker protection ensures that the generator and connected equipment are protected from overcurrents, which can damage the equipment and create a fire hazard. Verification involves testing the grounding system to ensure that it is properly installed and functioning correctly. It is recommended to consult with a qualified electrician to ensure proper installation and compliance with all applicable codes and standards. The NEC provides detailed requirements for grounding electrical systems, and it is important to follow these requirements to ensure safety. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding electrode conductor must be connected to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode must be located as close as practicable to the generator. The equipment grounding conductor must be sized in accordance with NEC Table 250.122. The equipment grounding conductor must be connected to the equipment grounding terminal of the generator and all connected equipment. The bonding jumper must be sized in accordance with NEC Table 250.102. The bonding jumper must be connected to the grounding electrode and the metal enclosure of the generator. The 400 amps breaker must be sized in accordance with NEC Article 240. The breaker must be rated to interrupt the available fault current at the generator terminals. Ground resistance should be measured using a ground tester. Continuity between all grounding conductors should be verified using a multimeter. Proper labeling of all grounding points should be provided to ensure that the grounding system can be easily inspected and maintained. In addition to the NEC requirements, local codes may also have specific requirements for grounding generators. It is important to check with the local authority having jurisdiction to ensure compliance with all applicable codes and standards. Grounding is a critical aspect of electrical safety, and it is important to ensure that the grounding system is properly installed and maintained. A properly installed grounding system will protect people from electrical shock and prevent damage to equipment. When selecting a generator, it is important to consider the grounding requirements. Some generators are equipped with a neutral bonded to the frame, while others require a separate grounding electrode. It is important to choose a generator that is compatible with the existing grounding system. When installing a generator, it is important to follow the manufacturer's instructions. The manufacturer's instructions will provide detailed information on how to ground the generator properly. Grounding is not something to be taken lightly. It is a critical safety measure that should be performed by a qualified electrician. If you are not comfortable working with electricity, it is best to leave the grounding to a professional. A properly grounded generator will provide years of safe and reliable service. Remember to always disconnect the power before working on any electrical equipment. Always use the proper tools and safety equipment. Never work on electrical equipment when it is wet or damp. If you are not sure how to do something, ask a qualified electrician for help. Electricity can be dangerous, so it is important to take precautions to protect yourself. Here's a more detailed breakdown of the grounding components. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically the neutral. Its size is based on the size of the service entrance conductors, ensuring a low impedance path for fault currents. The grounding electrode is a conductive object, such as a ground rod, metal water pipe, or ground plate, that is buried in the earth to provide a connection to the ground. The equipment grounding conductor provides a path for fault currents from electrical equipment back to the source, preventing dangerous voltage buildup on equipment enclosures. It is typically a wire or metal raceway. The bonding jumper is a conductor that connects different parts of the electrical system together, such as metal enclosures, raceways, and equipment frames, to ensure that they all are the same electrical potential. This minimizes the risk of electric shock. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding electrical systems to ensure safety and prevent electrical hazards. NEC Table 250.66 is used to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Table 250.102 is used to determine the minimum size of bonding jumpers based on the size of the circuit conductors. NEC Table 250.122 is used to determine the minimum size of equipment grounding conductors based on the size of the overcurrent protection device. NEC Article 250 covers the general requirements for grounding and bonding electrical systems. A ground tester is a device used to measure the resistance of the grounding system, ensuring that it is low enough to provide a safe path for fault currents. Continuity testing is performed to verify that all grounding conductors are properly connected and that there are no breaks in the grounding path. Proper labeling of grounding points is essential for identifying and maintaining the grounding system. Labels should clearly indicate the purpose of each grounding conductor and its connection point. Local codes may have additional requirements for grounding electrical systems, so it is important to consult with the local authority having jurisdiction. Some generators have a neutral bonded to the frame, which means that the neutral conductor is directly connected to the generator frame. In this case, a separate grounding electrode may not be required. Other generators require a separate grounding electrode, which must be installed in accordance with NEC and local codes. The manufacturer's instructions provide specific guidance on how to ground the generator properly, including the size and type of grounding conductors and electrodes to use. A qualified electrician has the knowledge and the experience to properly install and maintain a grounding system, ensuring that it meets all applicable codes and standards. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. The size of the overcurrent protection device must be properly matched to the size of the circuit conductors and the load being served. Ground fault circuit interrupters, or GFCIs, are used to protect people from electric shock by detecting ground faults and interrupting the circuit. GFCIs are typically required in wet locations, such as bathrooms and kitchens. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other electrical disturbances. SPD are typically installed at the service entrance and at individual pieces of equipment. Electrical safety is paramount, and it is important to take precautions to protect yourself and others from electrical hazards. Always disconnect the power before working on any electrical equipment. Use the proper tools and safety equipment. Never work on electrical equipment when it is wet or damp. If you are not sure how to do something, ask a qualified electrician for help. A properly installed and maintained grounding system is essential for electrical safety. By following the guidelines in the NEC and local codes, you can ensure that your electrical system is properly grounded and protected from electrical hazards. Understanding the role of each component, the importance of code compliance, and the need for professional expertise will contribute to a safer and more reliable electrical installation. In summary, grounding a 100W generator involves multiple steps and careful consideration of electrical codes. System grounding, generator grounding, conduit grounding, equipment grounding, and bonding must all be addressed. Verification through ground resistance testing, continuity checks, and proper labeling is crucial. Consulting with a qualified electrician is highly recommended to ensure compliance and safety. Consider the location of the generator in relation to the grounding electrode system. A shorter distance between the generator and the grounding electrode minimizes impedance and improves grounding effectiveness. Ensure that all grounding connections are mechanically sound and corrosion resistant. Use appropriate connectors and hardware to prevent loose connections or corrosion over time. Regularly inspect the grounding system for any signs of damage or deterioration. Replace any damaged components promptly to maintain the integrity of the grounding system. Keep accurate records of the grounding system, including the location of grounding electrodes, the size and type of grounding conductors, and any test results. This information will be helpful for future maintenance and troubleshooting. Consider the potential for ground loops when designing the grounding system. Ground loops can cause unwanted currents to flow in the grounding conductors, which can interfere with the operation of electrical equipment. Use appropriate techniques to minimize the risk of ground loops. Be aware of the different types of grounding electrodes available, such as ground rods, ground plates, and concrete encased electrodes. Choose the type of grounding electrode that is best suited for the soil conditions and the specific application. Ensure that the grounding electrode is installed deep enough to reach a stable ground potential. The depth of the grounding electrode will depend on the soil conditions and the local climate. Protect the grounding electrode from physical damage. Use a protective enclosure or barrier to prevent the grounding electrode from being damaged by vehicles, equipment, or other objects. Maintain a clear area around the grounding electrode to allow for inspection and maintenance. Remove any vegetation or debris that could interfere with the grounding electrode. Consider the impact of the grounding system on other electrical systems in the building. Ensure that the grounding system is compatible with other electrical systems and that it does not create any safety hazards. The 400 amps breaker, although seemingly straightforward, has nuances. It's essential to verify its interrupting rating matches the available fault current to the generator's output. An undersized breaker, even if it's within the ampacity rating, can fail catastrophically during a short circuit. Confirm the breaker's trip curve aligns with the generator's overload characteristics to prevent nuisance tripping or delayed response to actual faults. Moreover, consider the breaker's temperature rating. Ambient temperature can significantly affect breaker performance. A breaker in a hot environment may trip prematurely. Choose a breaker specifically designed for generator applications, as these often have enhanced features like arc flash mitigation and coordination capabilities. Lastly, ensure the breaker is properly labeled and integrated into the overall electrical system documentation. This facilitates quick identification and troubleshooting during maintenance or emergencies. The selection and installation of the 400 amps breaker requires careful attention to detail and adherence to industry best practices to ensure reliable and safe generator operation.